video, let's illustrate some inductor characteristics by showing some examples. In this first example, we have a 10 millihenry inductor, and current is flowing through that inductor given by this equation. Take note that this current starts at t equals 0. So first we're asked to plot the current so that you can see how it behaves from t equals 0 and onwards. And then we're required to find the voltage and the power of the inductor after 3 seconds. So this is the plot of the current. So as you can see, the current starts high at 10 amperes and then it decays as time progresses. So we use the relationship between the voltage and the current. VL equals di dt. So this is L, and this one is the derivative of the current. So that will give us this answer. Take note the voltage is negative. So that means that the current that enters the inductor is decreasing as shown by this curve. So a negative result means that the current is decreasing, and therefore the polarity of the voltage across the inductor with respect to the direction of the current must be reversed and should be this one. Okay, so the negative is facing the current where it enters, and the positive is on the other side. To get the current, we simply substitute t equals 3 seconds here, so we get this answer. And for power, we use the formula 1/2 Li squared, and that should give us this answer. In this second problem, we're given the voltage profile of the inductor starting at t equals 0. So here we see that the voltage is increasing, and then we're required to find the current that is passing through the inductor as a function of time, and then with the assumption that at t equals 0 the current is 1 ampere. So at the beginning the current is not 0 but has a value. So again, we use the relationship of the voltage and the current. To get the current, we use integration. So we integrate from 0 to t to get the accumulation of the current and plus the initial current so that we can get the total. So doing that will give you this. Doing the integration will give us this, and then that will give us the final answer, which is this one. So take note here, the current is also increasing. So that's consistent with our polarity of the voltage. So this is a positive. So therefore the current there should be increasing towards the positive polarity of the voltage. In this third and last example, we have a network where we have a capacitor and an inductor, and the circuit is under DC conditions. So meaning the circuit is already at steady state, And we're then asked to find the voltage across the capacitor and the current through the inductor, and also the energy stored um, in the capacitor at steady state. Here is the solution. Since the circuit is at steady state, this tells us that all voltages and currents are constants. So if the voltage is a constant across the capacitor, dVc dt should be equals to 0, and therefore the current through the capacitor is 0. If the current through the inductor is a constant, dIL dt is a 0, and therefore the uh, voltage across the inductor is a 0, which means that the inductor is acting like a short circuit. For the capacitor, since there's no current, the capacitor is acting like an open circuit. So we draw the circuit where the capacitor is an open circuit and the inductor a short circuit. We also show the current through the capacitor as 0, and the voltage across the inductor also is 0. Then we compute for the current I sub L. We notice that since the inductor is a short circuit, the 2 ohms and the 4 ohms are in parallel because they are connected to the same node. So they're connected to this node and to this node. Okay, so therefore they are in parallel. We then attempt to find the voltage across the capacitor by performing a KVL. So we find a loop to do that. So we use this loop. So we go around clockwise, starting here. So minus V sub C plus V sub L, but V sub L is 0. So we didn't write that anymore. Plus or minus the voltage across the 5 ohms. So this here, this is a minus, this is a plus, based on the direction of I sub C. But I sub C is a 0 as well, so therefore we get V sub C equals 0. We could have used this loop to get the V sub C, this loop here. So here, this is the plus, this is the minus. Well, the current through the 2 and 4 ohms are given by this. Okay, so this is also 2 here because this branch here is in series with the 2 ohms. Therefore, the current through the 2 ohms is also 2 amperes. 3 minus 2, that will give us 4 or 1 ampere through the 4 ohms. So doing a KVL around this loop, okay, so this loop does not contain any current source. So here, this is a plus, this is a minus. Uh, so this is the KVL equation. So starting here, we have plus V sub C. So we didn't include anymore the voltage drop across the 5 ohms because the current there is a 0. Minus 4 times the current, 1 ampere, and then plus 2 times the current, which is also 2 amperes. Equate that to 0, and we will also get V sub C equals to 0. To get the energy stored in the capacitor, we can use the formula 1 half CV squared, but the voltage of the capacitor is a 0, so therefore that will give us the energy stored as 0 joules.